Hello everyone. In this circuit, really simple, we're turning the potentiometer connected to A5 and the value changes, so essentially it's an analog read and it's printed onto the serial monitor. The only catch is that we're doing this through AVR assembler entirely. This project will focus on the concept of double dabble specifically. This section sets up the initial configuration and interrupt vectors for the AVR program. It declares main timer1 OVF vect and ADC vect as global symbols and define constants PLHI and PLLO for the timer1 preload to achieve a around 1 Hz interrupt. It also assigns aliases to registers util and offset for temporary use and ASCII conversion. The .org directives place the reset vector at 0x00, directing execution to main, and map the timer1 overflow and ADC interrupt vectors to their respective addresses. Finally, the code section starts at address 0x100 after the interrupt vector space. The main function serves as a starting point for the program. It calls several setup routines, IO setup, timer1 setup, ADC setup, and USART setup to configure the microcontroller's IO ports, timer1, analog to digital converter, ADC, and serial communication, so USART, respectively. After setup, the program enables global interrupts using SEI so that the interrupt service routines, ISRs, can be triggered. And finally, it enters an infinite loop followed by our jump loop, which keeps the program running without doing anything explicitly in the main loop. Everything important happens through interrupts. The USART setup configures the USART, so universal synchronous and asynchronous receiver transmitter, for serial communication at 9600 baud and using a 16 megahertz clock. It sets the baud rate by writing 103 to UBRROH and UBRROL. It then enables both the transmitter and receiver with UCSROB and sets the frame format to 8-bit data using UCSROC. This setup allows the microcontroller to send and receive data over the serial port. The I/O setup, so this function, it configures pin 13 as an output, so PB5, and it's commonly used to control an onboard LED, so which is what it's being used for in this case. So the instruction SPI DDRB 0x20 DDB5 sets the data direction register for PB5, enabling it for output, and allows the program to toggle the LED during runtime, typically just for like a visual indication that something like a interrupt or a conversion occurred, which is why I have it in my code. So the timer1 setup function, it initializes timer1 in normal mode with a 1024 prescaler, which is a divider to slow down the timer clock. It loads a preload value, so from constants PLHI and PLLO into the TCNT1H and TCNT1L registers so that timer1 overflows roughly once per second. It also enables the timer1 overflow interrupt by setting the TOI E1 bit in the TIMSK1 register, and this sets up the system to trigger an interrupt every second, acting as a periodic event source. So the ADC setup function, it sets up the analog to digital converter. So first it disables digital input buffers on all ADC pins to save power. It then configures the ADC to use AVCC as the reference voltage and selects channel ADC5, which is connected to A5. The ADC is enabled with a prescaler of 128 for accurate conversions, and a conversion is started. It waits for the first conversion to complete, clears the interrupt flag, and enables auto-triggering using timer1 overflows as the trigger source. And lastly, it enables ADC interrupts so that the ADC vect ISR runs when each conversion completes. So timer1 OVF vect, so this is the interrupt service routine for timer1 overflow. So when timer1 overflows about once per second, this function reloads the timer with the preload values PLHI and PLLO so that it continues operating on a 1 second interval. It then uses ret to reti to return from the interrupts and resume normal progress execution. For the ADC vect, this is the ISR for ADC conversion. When the ADC finishes converting an analog signal into a 10-bit binary number, this routine is triggered. It loads the result from ADCL and ADCH into registers R18 and R19, and then masks the upper bits of R19 to get a clean 10-bit result. It clears R20 to 22 for storing the BCD result, calls Dabble to convert the binary number into BCD format, and then calls display to send the value via UART. Finally, it toggles the onboard LED using SPI on pin B to give a visual cue that a conversion occurred. So the Dabble function implements the Dabble algorithm, which converts a binary number from R19 18 into a binary coded decimal format across 3 registers R22, 21, 20. It performs 16 iterations where each nibble 4-bit section is conditionally adjusted by adding 3 of the values greater than or equal to 5, and then the binary number is shifted into the BCD registers, and this algorithm is useful when displaying decimal values using only simple binary operations. And then the display function, it converts the BCD result from Dabble into ASCII characters and sends them over UART using a helper routine txchar. It uses the offset register set to the ASCII value of 0 to convert each 4-bit digit into its corresponding ASCII character. It reads both the high and low nibbles from each BCD register R22, 21, 20 and converts them to ASCII by adding the offset, and then sends them one at a time to the serial monitor, allowing the user to see the converted voltage value in decimal form. txchar function handles transmitting a single character over UART. It begins by loading the USART control and status register A, UCSR0A, into the util register to check the status of the transmit buffer. It then checks the UDRE0 bit, USART data register empty, and if this bit is not set, meaning the buffer is still full, the function jumps back and waits. Once the buffer is ready, it stores a character from register R24 into the UDR0 register to transmit it, and finally the function returns. Thanks for watching.